These are the sound notes that we did in science class. And if you have a science book, you can read about these in the science book, but not everyone got a science book, so we just went over it. So what is sound? A sound is a disturbance that travels through a medium as a longitudinal wave. Right, and we've talked a lot about longitudinal waves this past couple weeks. And so down here I wrote another way to say it. Sound waves are longitudinal waves that need a medium. So if you remember, we have waves, and then if it needs a medium or doesn't need a medium, if it does need it, we call it a mechanical wave. And there's different types of mechanical waves. The transverse waves that go up and down. There are surface waves, we talked briefly, that go like in circles, like water and ocean. And then the type that we're talking about now are longitudinal, and those are the ones that go forward and backwards. So here we have our longitudinal waves. They go forward and backwards in space. And longitudinal waves have different parts. So just like we learned in our last bit of notes here, we have compressions and rarefactions, places where the particles get close together and then they push the ones next to them, and that is how it transfers the energy through the medium. So here is a rarefaction. Particles are spread out, and here is a compression. So when this person is hitting the drum vibrates and it pushes the air particles out, and those are going to push the ones next to them out, and it's going to send these sound waves out. How can sound waves interact with their environment? So here's a few different things that can happen. The first one is absorption. So if you think of a sponge being absorbed, what happens? Waves go in, stay in. They don't come out. So here's a sound wave. It's going to hit this. Maybe it's like one of those noise canceling pads that you might find in like a recording studio. The sound wave will hit it, and then it kind of gets diffused inside there so it doesn't leave. And so those are nice to have maybe in a classroom. The other thing that waves can do is be reflected or reflection. And so what happens there is waves go in and they bounce back. And so here we have another surface, and here our wave's going to hit, and it's going to bounce back into the area. This is what usually happens in classrooms when your teachers ask you guys to get quiet and you're like, we're not being that loud. Well, your sound waves coming from your mouth are going to hit the wall and bounce back in, and it just echoes and it makes things louder. Transmitted is when waves go through. So if we have a medium here, and it can be any different kinds of things, and the wave hits, and instead of bouncing back or being absorbed, it just goes through it. And so when I'm talking in the air, right, if your medium's the air, that waves can be transmitted through there. It can be transmitted through water. If you go underwater and you scream, you can hear it from some distance. Even with the ground, if I'm hitting on the ground and you have your ear to the ground, that sound wave is going to travel through those mediums, and it's being transmitted. And finally, it can be diffracted, and that's when waves go around something. And so like if this is like a doorway, like you're in class, and the bell rings, it's gonna send those sound waves probably like this, but then they're going to bend and it's going to spread out, and it creates almost like a ripple effect, right? So your sound waves might have been traveling forward, but then when it goes through the opening, it's going to curve and spread out. And so those are 4 different ways waves can interact. Factors that affect the speed of sound. So hotter air, for example, sound travels faster. And the science behind that is the hotter matter is, the more loosely the particles are bouncing around and moving. And so then if you were to scream in a hot room versus a cold room, your sound waves are going to move quicker through the hotter air. So if temperature increases, so increase temperature, increase speed. And then the opposite is true. So if you decrease the temperature and it gets colder, the sound will travel slower. Next is states of matter. So solid, liquid, gas. If matter is gas, it's going to travel the fastest. Just kidding. If it's solid, it's going to travel the fastest. And so the reason why is because the particles are close together. And so if they're close together, it's going to send it through faster. Whereas if it's gas, it's more spread out. So it's the slowest. Which seems opposite, because over here we said that if it's the hotter temperature, the particles are moving faster, it's going to move quicker through. And logically, if we have solid, ice, liquid water, and gas, we think that, okay, well, higher temperature, higher speed, so gas must be the fastest, when in reality, it's not. And so sound travels fastest through solid and slowest in gas. Finally, density. So if I have two solid objects and one of them is very dense, so more dense, it's going to go slower. And if it's less dense, it's going to go faster. And so kind of back over here, if it's less dense, there's more space between the particles and it can go through. But if it's very, very tightly packed, then it's not going to go as fast. And this part is a little bit confusing. That's why this study guide might be helpful if you have any questions about that in the future. One thing that is more important than anything is that sound travels at different speeds. That's what you need to get out of this. Sound travels at different speeds through different mediums. Okay, last but not least, properties of sound, pitch and loudness. So pitch is affected by frequency of sound waves. So here we have a very high frequency wave, here we have a low frequency wave. So higher frequency, higher pitch. So it's very high, and then lower frequency, lower pitch. And frequency, we should know by now, the unit that we measure frequency is hertz. One thing we did talk about in class is that human hear 20 hertz through 20,000 hertz. Now, that doesn't mean that every human hears this range. I actually hear like 99 hertz to 14,000 hertz. And we did the hearing test in class, so if you want to watch the video that's attached to this, you can, to see what your hearing range is. But it is important to know that this is at least what humans are capable of hearing. Sounds beyond human hearing are called ultrasounds. And this is important. And so if you've heard of an ultrasound, maybe you think of a baby. Whenever somebody's pregnant, you go and you get an ultrasound. Yes, they use an ultrasound machine to take a sonogram. So what sonogram means is a sound picture. And the reason why we do this with pregnant women is that ultrasounds are harmless. So what happens is we use reflection, and whenever you make sound, those high frequency sound waves go through the skin and through the organs, and it bounces back at different rates, and it creates a sound picture that we can have. It's called a sonogram. The other property of sound is loudness, and so that is caused not by frequency but by amplitude. So here, say this is our rest position, a very high amplitude wave goes up very high, right? Whereas this is going to go, I tried to make these the same frequency. Here we have high amplitude equals loud. Then low amplitude is quiet. So the higher the amplitude of a sound wave, the louder it is, not necessarily the higher the pitch. So pitch is the frequency of the wave, amplitude is the loudness, and we measure this in decibels or dB. And so that's what we talked about for sound waves. If you have any questions, let me know.